Deep within the granite heart of California's mighty Sierra Nevada range is a valley like no other on Earth. Yosemite National Park contains some of the most awe-inspiring scenery imaginable. Rock walls carved by ancient rivers of ice rise nearly 3,000 feet above the valley floor. Hundreds of crystal-clear alpine lakes and mountain streams can be found in the 1,200 square mile park. Sprayed by 1,000-foot waterfalls and framed by monumental granite spires, a view in any direction will leave you breathless. The incredible beauty of Yosemite is also a geological masterpiece. Titanic forces operated over millions of years to create the unusual strength of its near-perfect granite, helping to form these magnificent landscapes. These processes by themselves are not unique, but their unrivaled interaction here in Yosemite has created a natural cathedral that draws millions of visitors from around the world.
Welcome to Yosemite National Park. Visitors come from all over the world to explore this wondrous landscape. Most people come to Yosemite and don't really think about the complex geologic processes that form this landscape. We'll be visiting several locations around the park to experience and highlight those geologic processes. The geologic history of Yosemite National Park really starts about 100 million years ago, when a slab of oceanic material was diving underneath the western edge of the North American continent. This process, called subduction, formed a chain of volcanoes similar to the Cascades all along the western margin of the North American continent. As volcanoes erupted on the surface, bodies of magma intruded and cooled deep within the crust. Those magma bodies cooled to become the plutons, the granitic rocks that we see exposed in Yosemite today. About 10 million years ago, the Sierra Nevada began to uplift. By that time, most of the remnants of that volcanic range had been long eroded away. With continued uplift, the mountains were able to capture large amounts of moisture coming off of the Pacific. Large river systems developed, including the Merced, which flows through Yosemite Valley. Those river systems carved deep, exposing those granitic plutons, and eventually formed the pathway for glaciers that straightened, widened, and deepened the valley of Yosemite.
Past ice ages produced glaciers that flowed out of high alpine areas of the Sierras. In some places, ice was more than 2,000 feet thick. These thousands of feet of glacial ice and its load of rock debris were highly effective in transforming the landscape. Running water in streams erodes a valley only at the bottom and produces a V-shaped profile. In contrast, glaciers widen and straighten the valley, producing a U-shaped profile. Evidence of Yosemite's glacial carving can be found throughout the park.
Over 4 million people come to Yosemite Valley every year to see the beautiful sights, but I bet not one of them actually comes to this spot. I am standing on a glacial moraine. This feature is very important in reconstructing the glacial history of Yosemite Valley. A glacier forms when large amounts of ice accumulate in the uplands and start to flow down valleys. Yosemite Valley has had a history of glaciation for about the last 2 million years, with 3 major glacial advances. The last glacial advance was the Tioga, and the glacier started to retreat about 18,000 years ago. And how far did it get? To this point. I can tell that because I'm standing on this mound that is a jumble of rocks. These rocks didn't just fall from the sides of the cliff beside me. These rocks came from several areas, including areas way up near Tuolumne Meadows, up in the highlands. There are rocks here that have large crystals of orthoclase. Others that just have kind of a salt and pepper appearance. Others that have large quartz crystals. They all come from different places in the park. And how did they get to this spot? The glacier brought them. Now, streams also carry rocks a long way, but streams have a different way of depositing sediments. Streams typically deposit sediments in layers. Glaciers just drop their material. And glaciers can carry huge chunks like this rock behind me. And yet there are very small pieces of rock that litter the ground as well. So this jumble of rocks was deposited at the toe of the glacier.
Eventually, the climate warmed abruptly and the Tioga Glacier retreated. The remaining moraine acted like a dam, creating Lake Yosemite. Over time, the lake filled with sediments, producing the relatively level valley floor we see today. Yosemite is famous for its high concentration of waterfalls. More than 24 may be found flowing during the spring snowmelt. Waterfalls leaping out from a valley's walls have long been considered evidence of a glacial origin for the valley.
Yosemite Falls is the most famous waterfall in Yosemite National Park. However, the waterfall that most visitors see when they first get to the park is Bridal Veil Falls. Bridal Veil Falls is a spectacular example of a hanging waterfall. Hanging waterfalls form when glaciers flow down a main valley, like Yosemite Valley, and those large glaciers rapidly deepen the trough. The tributary that Bridal Veil Falls is coming out of has a smaller glacier, which doesn't cut down nearly as fast. The main glacier not only deepens the valley, but widens the valley. So once the ice melts back, Bridal Veil Valley is left hanging up above the main valley.
While Bridal Veil Falls plunges from a U-shaped glacial valley, Yosemite Falls has a distinctly different appearance. Yosemite Creek entered the Yosemite Valley through a steep-sided canyon before glaciers covered the region. After glaciers deepened Yosemite Valley and reshaped the uplands, the path of Yosemite Creek was changed. It now plunges into the valley just east of its original position.
Yosemite Falls is one of the most recognizable features of the park. Yosemite Creek plunges 2,425 feet in a series of 3 steps down to the bottom of Yosemite Valley. During the spring, when Yosemite Creek is fed by snowmelt, the sound of the falls can be heard in an enormous roar throughout the entire valley. However, in the fall, the time of year that we're here, it's often barely a trickle. Today, we actually are lucky to have a very nice view of the falls because of a recent storm that passed by that fed the headwaters of Yosemite Creek. But why is Yosemite Creek falling in 3 steps? It has to do with the fractures that occur throughout the valley. Granitic rock and any type of rock, through the forces of tectonics over time, will fracture. Those fractures are often parallel to each other and occur in a variety of orientations. The orientation of Yosemite Creek itself, almost due north, follows a large regional fracture into its watershed up and beyond Tioga Road. There's another large regional fracture system that parallels Yosemite Valley.
The path of the Merced River was guided by this fracture system. As ice later widened the valley, rock broke up along parallel fractures to produce the series of steps over which Yosemite Creek cascades. Fractures also played an important role in creating Yosemite's most famous landmark. At the head of the valley, as if on a pedestal, stands Half Dome, one of the most colossal and iconic rock monuments in the world. As large as 1,000 football stadiums, its northwest face is a 2,000-foot vertical drop. Half Dome was originally called Tisaak, meaning cleft rock in the language of the local Native Americans. Its sheer granite face looks as though it were sliced clean by an enormous knife from the heavens.
One of the most frequently asked questions by visitors to Yosemite National Park is, where's the other half to Half Dome? Well, during the peak of glaciation, about 1 million years ago, in what we call the Sherwin Advance, ice flowed out of Tuolumne Meadows and down Tenaya Canyon in front of a long, high ridge of granite. That river of ice deepened and widened the valley, and as it did, it took advantage of fractures that paralleled Tenaya Canyon and were right in front of Half Dome. Rock was carved off and scraped off and carried away from that long granite ridge and carried down the valley. So it is estimated that what we now call today as Half Dome actually is still 80% of that original long, low ridge. It's just that the fracture that parallels the northwest face makes it appear that there used to be much more there.
Looking eastward from the west end of the valley, we see the immense profile of El Capitan, one of the sheerest cliffs in the world. 3 billion cubic feet of granite project boldly more than a half-mile above the valley floor, the result of limited fracturing within its structure.
El Capitan is famous for its massive bulk and sheer vertical 3,000-foot cliff that soars above the valley. It is a particularly durable granite, largely unbroken, that withstands the erosion of, in the past, glacial ice and now river erosion. The El Capitan granite was emplaced 103 million years ago. It is largely quartz, feldspar, with large biotite and a little bit of hornblende, and is the primary rock that makes up this area crossing Yosemite Valley. Compare that to the granite of Half Dome, which has less quartz, less biotite, and much more very well-formed crystals of hornblende.
Although glaciers are responsible for much of the Yosemite landscape, there is another process that shaped the high rounded granite domes. The dome surfaces reveal onion-like sheets of rock, which break up and slide off under the force of gravity.
I'm standing on top of Sentinel Dome at a little over 8,000 feet. Most people come up here and think that this rounded surface must have been carved by glaciers. However, even at the height of glaciation, Sentinel Dome, North Dome, and Half Dome peaked up above the glacial ice. So how did this surface become rounded? The process that is in action here is called exfoliation. It begins when magma intruded deep within the crust, and that magma was solidified into what we call a pluton. That hard rock, even at depth, was under tremendous pressure. Over long periods of time, kilometers of rock was stripped off. And as that rock was elevated near the surface, the pressure of all that rock was released, and this solid rock was able to expand. The problem, though, with trying to make a solid expand is that it can't stretch. It has to actually fracture. Those fractures form parallel to the surface. These fractures then allow water to seep in, flow, allow trees and their roots to grow, and eventually sheets of this rock fall off in the process that we do call exfoliation. These slabs of rock, over time, as they fall off, smooth and round the surface.
Up in the high country along Tioga Pass Road, you can find rounded granite surfaces worn smooth by a glacier.
Pothole Dome is a classic example of a large piece of granite that has been overrun and carved by a glacier. This whole area of Tuolumne Meadows lay under a very large ice sheet. This ice was up to about 2,000 feet thick. As that ice flowed, it carved and shaped this whole area. Glaciers flowed out of that ice sheet all the way down Tenaya Canyon and into Yosemite Valley. The length of the glacier was up to 60 miles, the largest in the Sierra Nevada. So how do we know that a glacier carved this area and flowed over Pothole Dome? Well, the evidence is all around us. Next to me is what we call a glacial erratic. An erratic is a rock left behind by the glacier that came from somewhere else. This rock was left here as the glacier retreated. In this case, this erratic is made of the same Cathedral Peak granite that Pothole Dome itself is made of. However, if we looked around, we could find other erratics made of different types of granitic material as well. Besides erratics, there are several other clues that a glacier flowed over Pothole Dome. There are scratches that are very well preserved in some what we call dikes, intrusions of very fine-grained, hard, quartz-rich material that streak through this Cathedral Peak granite. There are also grooves and glacial polish. Some of the areas of this dome look like a mirror. There are what we call chatter marks, curved, arcing, almost incisions where the glacier had hold of a large rock and lurched forward, and that rock was a tool that it used to carve a chunk out of the dome.
Since the glaciers retreated around 15,000 years ago, rockfalls have been the major force that continues to shape the Yosemite Valley. Historical records indicate that at least 600 rockfalls have occurred in the park during the past 150 years. Every significant rockfall in Yosemite Valley has originated in vulnerable fractured rock from above the level of the Tioga Glacier. Frost wedging is one of the primary forces that cause rockfalls. Water seeps into fractures in the rock and freezes, causing the fractures in the rock to expand. This can incrementally pry loose rocks away from cliff faces. Other triggering mechanisms like rain, vegetation, and earthquakes can create the final forces that cause unstable rocks to fall. In recent years, Yosemite has experienced some huge rockfalls that released well over 100,000 tons of material. But most are relatively small and gradually build up a cone of debris below the most active sites. Given the nature of the geologic setting, it is inevitable that rockfalls will continue as part of the ongoing geologic processes, posing potential hazards to park visitors. Yosemite National Park is an extraordinary place that resonates with visitors as few other locations do. The grandeur of its beauty leaves lasting images in the mind that are not easily forgotten. Whether we realize it or not, it's the geology of Yosemite that impacts us. As we stand dwarfed in the presence of nature's cathedrals, we are in awe of the immense size and power that surrounds us. A brief respite from our fast-paced lives to witness such grandeur reminds us of our connection with the natural world.